Why distinguish ideal versus real inductance and capacitance? Imagine building a circuit and expecting it to behave perfectly, like a simple math problem. But in reality, components don't always follow those perfect rules. That's why understanding the difference between ideal and real inductance and capacitance is so important. Ideal inductors and capacitors are like perfect models that only do one thing. An ideal inductor stores energy in a magnetic field and has no resistance or other effects. An ideal capacitor stores energy in an electric field and has no resistance or parasitic elements. These models make calculations easier and help us understand the basic behavior of circuits. But real inductors and capacitors are different. They are made with physical materials and have some unwanted traits. For example, real inductors have resistance in their wire coils. This resistance causes energy to turn into heat, which wastes power. Real capacitors have something called equivalent series resistance, which also causes energy loss and affects how they work at high frequencies. Another difference is parasitic capacitance and inductance. Real inductors have tiny capacitances between their windings. These parasitic capacitances can make the inductor behave like a resonant circuit at certain frequencies. Similarly, real capacitors have parasitic inductance from their leads and internal structure, which can change their behavior at high frequencies. Frequency plays a big role here. Ideal inductors' impedance increases steadily as frequency rises, but real inductors can reach a point called the self-resonant frequency. At this point, their parasitic capacitance cancels out their inductance, causing a drop in their ability to oppose changes in current. Capacitors also have a resonance point where they switch from acting like a capacitor to acting like an inductor. Energy loss is another factor. Real components lose some energy as heat, which reduces efficiency. For high-frequency or high-power circuits, these losses can be significant. Ignoring these effects can lead to circuits that don't work as expected or fail prematurely. Knowing the difference helps engineers design better circuits. Using only ideal models might lead to mistakes, especially in high-frequency applications like radio frequency circuits. Engineers need to consider parasitic effects when choosing components, ensuring they work well at the intended frequencies. For example, selecting an inductor with a high enough self-resonant frequency prevents unwanted resonances. Designing circuits also involves layout and thermal management. Understanding real component behavior guides decisions on how to place components and how to keep them cool. This makes the circuit more reliable and performs closer to expectations. In practical terms, if you're working with radio frequency circuits, knowing the self-resonant frequency of an inductor tells you the highest frequency it can handle without losing its inductive properties. Ignoring this can cause your circuit to malfunction or produce poor signals. So, distinguishing ideal from real inductance and capacitance is about more than just accuracy. It's about making sure your circuit works as planned in the real world. It helps you pick the right parts, design better layouts, and understand how components will behave under different conditions. This knowledge is fundamental in electromagnetism and fields where precise control of electrical energy is needed.